Let's recap sequences and series just for a minute here, and then we'll start talking about 9.2 homework. So in 9.1, we talked about sequences. And remember, sequences are just a list of numbers. A1, comma, A2, comma, A3, dot, 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 A sub n, dot, dot, dot. Okay? It goes on to infinity. What we found is that if we can look at the limit as n goes to infinity of the nth term and it equals some number, that means that that is what this sequence is approaching and it is converging to that number. So we could say if the limit of the nth term equals some L, then the sequence converges to L. Okay? That was for sequences. But when we get to series, which are A1 plus A2 plus A3 plus dot, 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 plus A sub n plus dot, 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 when we're talking about series like that, infinite series, if the limit as n goes to infinity of our A sub n equals a number, that means the series diverges. Okay, because you basically would be adding up that same number. Like let's say it was 2/3. You basically are, approaching values that are 2/3 and you just keep adding 2/3. So that makes sense then that for a series, so you really have to look and see what you have. For a series, if your limit of your nth term equals some value, then it diverges. Now, if your limit, and you have a series, if your limit as n goes to infinity of your nth term equals 0, then your series might converge. It does not absolutely mean that it converges. It might converge. Now, why would that be? Well, because as you're adding on, you're basically just adding on 0. So you're continuing to add 0, add 0, add 0. So that's why in these early stages, before we have learned more of our convergence and divergence theorems, then right now, this is all we know, okay? So if you have a series and you take the limit of the nth term and you get a number, you know it diverges. If you have a series, you take the limit of the nth number and it equals 0, it might converge. You're going to have to do some more investigating to find out whether it converges or not, okay? So that's where we are so far, kind of in a nutshell, up to this point. So if you get something like number 8 from your 9.2 homework, and you've got summation n equals 1 to infinity, 4 to the n plus 1 over 5 to the n, and they want you to determine whether the following series converges or diverges and justify your answer, what I would do on one like this, because it looks very much like a geometric series. So I'm going to start manipulating this to see if I can figure out what kind of series I have. It starts with 1, so this is going to have to be n minus 1. We want, because it told us that, it told us in our definition that if we have a geometric series, by definition, it was either going to be the summation from n equals 1 to infinity, a1 times r to the n minus 1, or it was going to be summation n equals 0 to infinity, a1 times r to the n. Okay, so it's either going to be r to the n minus 1 or r to the n. It's not going to be r to the n plus 1, right? And we can't change n equals 1 here. So we're wanting to take this and somehow write it differently. So you want to just begin by thinking, oh, well, this would be 4 times 4 to the n over 5 to the n. But this still starts at 1. So I still don't have what, I mean, if it started at 0, this would be an easy problem because I would just be able to say 4 times 4/5 to the n. But it doesn't start at 0, it starts at 1. So I need this to be n minus 1. So how do I do that? How do I get that to be n minus 1? And so if you like pull that out, if you made this 16/5 and made this 4/5 to the n minus 1, are you still going to have the same thing? So in essence, what I did was I took this 4 and I thought, wait a minute, if this was 4, if I wanted this to be 4 to the n minus 1, I would have a 4, I would have to take a 4 out. Sorry. So think of it like this, like this would be if I took another 4 out, 4 to the 1 out, I'd be left with 4 to the n minus 1. Does that make sense? Because if I took this thing and added all my exponents, I would have 4 to the n. And then this one, if I took a 5 out, 5 to the 1, this would become 5 to the n minus 1. And so this should still equal 5 to the n because when I have the same base and I'm multiplying, I add my exponents. So this becomes, if I take these two, I've got 16 times 4 to the n minus 1 over 5 times 5 to the n minus 1. That gives me 16/5 times 4/5 to the n minus 1, okay? And we wanted to get it to that point because now I have a geometric. So this right here has now shown me that I have a geometric series because it was going from n equals 1 to infinity, and my a sub 1 is 16/5 and my r is 4/5. Since 4/5 is less than 1, oops, sorry, wrote 0. Since 4/5 is less than 1, the series converges. And, excuse me, the sum of the nth term, a over 1 minus r, is going to be 16/5 over 1 minus 4/5. So that's going to be 16/5 over 1/5. So that's going to be 16. Okay? Because we knew it was a geometric series. We knew that we had to get it into either this format to see our a sub 1 and our r, or we had to get it into this format to see our a sub 1 and r. Okay? And so what we did was we manipulated it. It still equaled the same thing. We just manipulated it a little bit, and we're able to see what our a sub 1 was and what our r was, and then we knew we had a geometric series. Okay? So that is just kind of an idea of what's going on with